Testing. Okay, working. Alright, Chapter 6. Optical source fiber optic transmitters. Learning objectives upon completion of the chapter, you should be able to do the following. Explain principal property for the optical source of fiber optic transmitters. Discover the optical emission property for the semiconductor emitting diodes and laser diodes. Describe the operational difference between the surface emitting LEDs, edge emitting LEDs, and superluminescent diodes and laser diodes. Describe typical fiber optic transmitter packages. Introduction. Optical source of fiber optic transmitter. For the chapter 1 taught you the fiber optic data link has three basic functions. One of the functions fiber optic data link must convert the electrical signal with the optical signal, permitting transfer of the data along with the optical fiber. The fiber optic device is responsible for the signal conversion with the fiber optic transmitter. The fiber optic transmitter is a hybrid device that converts the electrical signal and optical signal, launches the optical signal into the optical fiber. The fiber optic transmitter consists of an interface circuit, source driver kit circuit, optical source for the interface circuit accepts the incoming electrical signal and processes to make it compatible with the source drive circuit. The source drive circuit intensity modulates the operator source of the varying of the current through the source. The optical source converts electrical energy into optical energy light emitted by an optical source launching coupled into the optical fiber from the transmission. The fiber optic data link the performance depends on the amount of the optical power light launched into the optical fiber. The chapter attempts to provide understanding of the light generating mechanism with the maintained optical sources used in fiber optics. Optical source property development is efficient for semiconductor optical source along with low loss optical fibers led with a substantial improvement of fiber optic communication. Semiconductor optical losses sources have physical characteristics and performance properties necessary for the successful implementation of the fiber optic systems. It's desired that the optical sources be compatible in size loss low loss optical fibers by having small lighting emitting area capable of launching it into the fiber lines. Sufficient optical power with the optical fiber to overcome the fiber attenuation and connection loss, allowing the signal detection at the receiver. Emit light wavelengths to minimize the optical fiber loss. The dispersion optical source should have narrow spectrum with width to minimize the dispersion. The direct modulation optical output power maintain stable operation, changing environmental conditions such as temperature, cost less, be more reliable electrical device. Permanent fiber optic communication system to complete with a conventional system. Semiconductor optical source that's suitable for the fiber optic systems range from inexpensive light emitting diodes to more expensive semiconductor lasers. Semiconductor light emitting diodes and laser diodes are principal light sources used in fiber optics. Operating wavelength. The fiber optic communication system operates at 850 nanometers to 1300 nanometers and 1550 nanometers wavelength windows. Semiconductor sources that are designed to operate with wavelengths to minimize the optical fiber absorption, maximize the system bandwidth. Design with the optical source to operate the specific wavelengths absorption over the impurity of the optical fiber. The hydroxyl ions can be minimizing the system bandwidth involved with the designing optical fiber to sort of minimizing chromatic intermedial dispersion at the intended operational wavelength. Intentionally, the material property of the semiconductor optical sources provide optical emission with the 850 nanometer wavelength region and the 850 nanometer operation wavelength avoids fiber absorption of the OH impurities near the 900 nanometer wavelength. Light source of the 850 nanometer systems originally semiconductor light emitting diodes, lasers. Currently, most of the 850 nanometer system of the LEDs are light sources. The LEDs operate from 850 nanometers, provide sufficient optical power with a short distance low bandwidth system. However, the multi-mode fibers dispersion relatively high fiber attenuation and the LEDs relatively low optical output power prevent the use of the power device for the long distance higher band systems. First, developing allowing the operational wavelength to move to 850 nanometer 1300 nanometers with the introduction of multi-mode gradual integrated index fiber. The multi-mode graded index fiber has substantial lower intermodule dispersion. Multi-mode stepping index fiber the system operating within 850 nanometers can take full advantage of the fiber's low intermodule dispersion because of the high chromatic dispersion at 850 nanometers. However, the use of the multi-mode grade index fibers allow the 850 nanometers LEDs to operate satisfactory short distance higher bandwidth system. Following the enhancement of the multi-mode fiber to design the next generation LEDs was designed to provide optical emissions in the 1300 nanometer region. Multi-mode grade index fiber systems used in LEDs can operate with long distance higher bandwidth of the 850 nanometer system. Longer distances and higher bandwidth are possible because the fiber material losses and dispersion are significantly reduced at 1300 nanometer region. Advanced single mode of the fiber design construction with sped the development of the semiconductor LEDs and laser devices. Optimized by single mode fiber. The single mode fiber, the low dispersion values. However, the LEDs were unable to fulfill the launch sufficient optical power into the single mode fibers. for long haul, very high bandwidth communication system. Now, semiconductor LEDs and laser devices capable of operating single mode. The fibers of 1300 nanometers were developed to advantage for the single mode fiber to very low value of operation dispersion. Additional LEDs and laser devices operating at 1515 nanometers were developed to make the advantage for the fiber low loss. Semiconductor light emitting diodes and laser diodes. Semiconductor LEDs emit the incoherent light with the spontaneous emission of the light with the semiconductor LED process light. The waves lack the fixed phase relationship. Light waves lack the fixed phase relationship that refer to the incoherent light. Spontaneous emission of the light was discussed in more detail and later in the chapter. The LED single mode system is severely limited because they emit unfocused incoherent light. Even LEDs develop a single mode system that are unable to launch sufficient optical power into the single mode fibers for many of the applications. LEDs are preferable optical source of a multi-mode system because they can launch sufficient power to at a lower cost of semiconductors or laser devices. Semiconductor-related devices emit the current light. The laser device produces a light wave with a fixed phase relationship, both spatial and temporal, between the points of the electromagnetic wave. The light waves have the fixed phase relationship preferred to the coherent light with the simulated emissions light that I discussed later in this chapter. Since semiconductor light laser devices emit more focused light than LEDs, they are able to launch optical power in both single and multi-mode optical fibers. However, the laser device is usually only in a single mode fiber system because they require more complex driver circuitry then costs more than the LEDs. Optical power produced the optical source can range with the microwatts. For LEDs, tens of the milliwatts of the semiconductor laser devices. However, not possible to effectively couple all the available optical power with the optical fiber transmission. The optical power coupled with the fiber. Relevant optical power is dependent on the following factors: the angles over which the light is emitted, but the source of the light emitting area relative to the fiber core side of the alignment of the source of the fiber and the source and fiber, the coupling character of the fiber, such as the numerical arbitrary with a reflective index profile. Typically, semiconductor laser emitting spread over the angle at 10 to 15 degrees. Semiconductor LEDs emit the light spread out of even large angles. Coupling left with several decibels can easily occur. Coupling light with the optical source of the fiber, especially LEDs, source to fiber. The efficiency measured with the relatively optical power with the coupling. The efficiency depends on the type of the fiber attached with the optical source. The coupling efficiency also depends on coupling techniques. Source to fiber, the coupling involved the even enter flat fiber and face over emitting region with light source of the fiber face and face directly placed over the source emitting the region and refer to the coupling. The source output light with a pattern is larger than the fiber's acceptance pattern. So the fiber coupling efficiency might be provided by placing a small lens between the source and the fiber. Lensing schemes improve the coupling efficiency of coupling the LED and laser devices optical fibers. Semiconductor material and device operation principle. Understanding the optical emission semiconductor laser and LEDs required knowledge of the semiconductor material device properties, providing a couple of descriptions of semiconductor properties beyond the scope of the introductory manual. In this chapter, we only discover the general properties of the semiconductor LEDs and laser devices. Semiconductor source of the diodes will also characterize the typical diodes. However, the construction includes the special layer of the active layer where they emit photons, light particles, where the current passes through the laser particle and properties of the semiconductor determine the materials used for the layering materials within the semiconductor. Silicon and gallium arsenide are the two most common semiconductor materials used within electronic electro-optic device. In some cases, other elements such as aluminum and indium phosphorus are added to the base of the semiconductor material to modify the semiconductor properties. The elements are called dopants. Current flowing through semiconductor optical source of the cover of the product produce light with in depth of the description of either the two possibilities occur beyond the scope of the module. However, we will discuss elementary description in the following paragraphs. LED generally produce the light through spontaneous emission current through damping through them. The spontaneous emission random generation photons with the active layer of the LED. The emitted photons move random directions. Only in a certain percentage of the photons exist with the semiconductor coupling into the fiber. Many of the photons absorb the LED materials. Energy dissipated with the process cover the light out of the LED to be incoherent, have the broad spectral width and head and wide output pattern. Laser diodes are much more complex than the LEDs. The lasers are acronym in light amplification by stimulated emission of the radiation. Laser diodes reproduce the light through the stimulated emission with the current pass through them. Stimulated emissions describe them how light is produced, the type of the laser. In the laser diode, photons initially produce the spontaneous emission interaction with the laser material. Produce additional protons occur with the active area of the diode called the laser cavity. The process does not affect the original photon. Stimulated photons have many of the some properties of the wavelength direction favor the original photon. As the LEDs are not all the photons produced that are emitted with the laser diode, some of the photons are absorbed and dissipated as heat. The emission process and physical character of the diodes called the light output with a coherent narrow spectral width and narrow output pattern. It's important to note that the LEDs and laser diodes all have electrical energy not converted all electrical energy is not converted into optical energy. A substantial portion of the converted to heat. The different LED laser diode structures converting differing amount of electrical energy to optical energy. Light emitting diodes. A light emitting diode is a semiconductor provided that is incoherent light through the spontaneous emission when the current is passed through it. The typical LEDs for the 850 nanometer region are fabricated with a GaAs or gallium arsenide, aluminum, gallium, and arsenide. LEDs are for 13 nanometers of 1550 nanometer region with fabricated UV and the gallium arsenide phosphorus are in something phosphorus. Basic LEDs typically with the use of fiber optic communication system lighting, surface lighting LED, or SLED, the emitting edge emitting LED, super lucent diode. The LED performs the difference of the design of the dedicated device of the appropriate intended application for the short distance 0 to 3 kilometers. Low data rate fiber optic systems of the surface light emitting diode and the edge emitting light or diode are preferred optical surfaces, such as the surface light emitting diode operate efficiently with a bit rate of 250 megabytes per second because of the surface light emitting diode emit light over the wide area of the wide far field angle with almost exclusively use the multi-mode system. For medium distance, medium data systems, edge light emitting diodes are performed. Edge light emitting diodes may modulate with a rate of up to 400 megabits 400 megabits a second. Edge limiting diodes may be used with both single and multi-mode fiber systems. Some of both surface light emitting diodes and edge limiting diodes are used with the long distance and high data rate systems. Surface light diodes and edge light emitting diodes based on design operative with the superluminescent mode. With a further discussion, superluminescent is provided in the chapter. Superluminescent diodes may be mounted by bit rates of 400 over 400 bits per megabytes a second. Or a surface emitting light LED. Surface emitting light ED shown figure 6.1 are known as the burst LED in honor of the CA burst. Through the developed the surface light emitting diode, the surface of the primary active region the limited is all circular area of 200 meters, 550 micrometers in the diameter. The active region of the portion of the LED whose photons are emitted to the primary active region that is below the surface of the semiconductor substrate and perpendicular to the axis of the fiber as well. The edge for the substrate will allow the direct coupling of the emitted light to the optical fiber. The edge will also allows the optical fiber to come in close contact with the emitting surface. In addition, epoxy resin binds the optical fiber to the surface of the light emitting diode, reduce the refractive index mismatch, and increase the coupling efficiency. Shift the optical fiber, the epoxy resin metallization, etch well, the negative type gallium arsenide substrate, aluminum gallium arsenide. Take the tip of positive, negative or positive type gallium arsenide, the positive type aluminum gallium arsenide, positive type aluminum gallium arsenide, metal sink, heat sink, circular contact region, primary active region, double heterojunction layers. The edge emitting light emitting diodes depend on the optical surface of the long distance higher band system operating along with the wavelengths led to the development of edge emitting diodes. Show the figure 6.2 that show the typical edge emitting diode structure. Show the different layer of the semiconductor material with the edge light emitting diode with the primary active region with the edge light emitting diode in the narrow strip of which lies below. Strip of the semiconductor substrate, but the semiconductor substrate is cut and polished from the start. Strip runs through the front to back of the device and polished over the cut surface of each end of the strap are called facets. Show the example of the edge emitting diode stripe contact metallization silicon oxide, negative pipe, inert gallium arsenide, negative inert phosphorus, inert type, and positive type, inert gas, arsenum, positive type, negative type, inert phosphorus, negative type, inert substrate, metal heat sink, double heater junction, optical output beam, incoherent. The edge light emitting diode rear facet, the high reflective front facet, anti-reflection coated with the rear of the facet, reflect with the light propagation toward the right end of the face back to the front face of the facet by coating the front facet with the anti-reflection material of the front facet to reduce the optical feedback, allow the light emission edge light emitting diodes emitting light only through the front facet. Edge light emit light narrow emissions, allowing a better source of the fiber coupling. They couple more into the small numerical arbitrary fibers of the surface light emitting diode. The edge light emitting diode couple enough power into a single mode fibers for the some application. Edge light emitting diodes and power with a narrow spectral range of the surface light emitting diodes. However, edge light emitting diodes typically are more sensitive to the temperature fluctuations of surface light emitting diodes. Alright, your laser diodes. A laser device produced with a group optical radiation product with the simulated emission. It is necessary to contain photons produced with the simulated emission of the laser active region. Figure 6.3 show the optical cave with the amplification containing emitted photons and placed in one of the reflecting mirror at each of the end of the amplifying medium. One mirror was made particularly and partially reflecting some of the radiation can escape from the cavity, coupling to an optical fiber. The reflect back and forth from the cavity from lasers occur with the optical gain of the selected mode of the image. We can see the optical loss from doing one round from the through the cavity. The process is referred to the optical feedback. The lasing threshold of the laser on the lowest drive current level of the output laser per resolve of the primary from stimulated emissions rather than stimulus emission. Figure 6.4 illustrates the transition of the stimulus emission with stimulated emission, plotting relative to the optical output power input drive current with the semiconductor laser device. Lowest current at which stimulated emissions exceed the spontaneous emission threshold current, but there are three. The threshold current is reached optical input with the power increase the output. Slightly with a smile increase the drive current. However, after the threshold current is reached, the optical out power increases significantly, which will change in drive currents. Optical output power relative to stimulated emission, spontaneous emission threshold current, input drive current. Many types of materials, including gas, liquid, and semiconductors, can form a lasing medium. However, the chapter will only discuss semiconductor laser diodes. Semiconductor laser diodes are primary laser for the fiber optic laser diodes emit light with a highly monochromatic, very directional because the laser device output with a narrow spectrum of the width and with a small output beam angle. Semiconductor laser device geometry. Some of the edge light emitting diode, the light guiding region is surrounded by the active region. Optical feedback is established, making the from the fossil partially reflective. The chapter provides no diagram detailing laser device structure because they are similar to the edge light emitting diodes in design. The rear facet typically can go to the reflective layers so that all the light training of the facet is reflected back into the active region. The front facet is typically left uncoated, with the most of the light is emitted by increasing the drive current of the diode becomes the laser at current below the threshold of the light laser device functions as edge light emitting diode. The optimized frequency response of the laser diodes often biased above the laser threshold. The result of the laser device fiber optic system light is modulated between the high power level and the low power level, but never shut off of the light device. Laser never shut off. Laser devices typically can be modulated frequency of the 2 GHz. Some lasers are capable of being modulated with frequencies of 20 GHz. So there's several important difference with the laser devices and the LEDs. One of the LEDs usually lack reflective passive. In some cases, designed suppress the reflection back into the active region. Another is that the laser tends to operate with a higher drive currents to produce light. The higher drive current is a result of a more complicated drive circuit with a more high heat dissipation in the device. The laser device is almost more temperature sensitive than surface LEDs and edge limit LEDs. Increase the laser for the temperature significantly reduce laser output power. Increase the laser temperature beyond the certain limits, with the resulting loss of the lasing laser issue. The many of the application temperature for the laser must be controlled. Typical electron coolers called thermoelectric coolers are used to cool laser devices in system applications. Luminescent diode, superluminescent diode. Superluminescent with the spontaneous emission of the edge light emitting diodes experience gain due to the high injected current. The reflection from the fastest superluminescent diodes are differentiated with both conventional LEDs and laser devices. Although output is not coherent, the superluminescent diodes emit light through the constant amplified spontaneous emission spectral width in the beam, and the superluminescent diodes are narrower than the conventional LEDs and wider than the laser devices. Superluminescent diode is essential for the combination of the lighter edge light emitting diodes. Superluminescent diodes are similar to geometry to the laser built when they have no optical feedback mechanism required for the laser diode stimulated emission with the achieve lasing. Superluminescent diodes have structural features similar to the edge light emitting diode with the super lasing action by reducing the reflective facet. Super light emitting diodes essentially highly optimized the edge light emitting diodes, with the superluminescent diodes operate like edge light emitting diodes. The low current level of optical power increase with the superlinear spectral width narrow with the higher current with optical gain result of the higher injection current to the cause of the superlinear power increase with the narrow and spectral width. The advantages of superluminescent diodes are conventional with the LEDs. Light emitting diodes include the high coupled power, narrow spectral width, great bandwidth. The disadvantage include the nonlinear power control current characteristics higher than temperature sensitivity, low reliability. Alright, fiber optic transmitters. The stated previously fiber optic transmitter hybrid electro-optic device that converts electrical and signal the optical signal launch optical signal the optical fiber. The fiber optic transmitter consists of the interface circuit that source the drive circuit the optical source. Interface circuit accepts the incoming electrical signal profit that makes it reliable with the source of the drive circuit, with the source drive circuit intensive with the modulated with the optical source varying with the current through the optical signal is coupled with the optical fiber through the transmitter output interface. Although semiconductors, LEDs, and laser devices may have a similarity with the unique transmitter design result from the difference between the LEDs and laser devices. Transmitter's design compensates for the difference in optical output, but the response time, linearity, thermal behavior between the LED and the laser device to ensure the proper system operation. Nonlinear caused by junction-headed LEDs, instability, laser device sensitivity, use of linearizing circuit with the transmitter in some cases. Fiber optic transmitters use the laser device require more complex circuitry, but the transmitter with the LEDs because of the requirements of the digital system of the drive circuitry with the switch for the optical output on high speeds response logical voltage input with the source of the drive circuit because of the laser device are thresholds. Laser devices are supplied with the bias just below the threshold in the off state of the basis is often referred to as the pre-bias. The one response, one reason for the pre-bias with the laser device is to reduce the turn-on delay to digital system. Both the laser devices transmitter contain output with power control circuitry. The compensate with the temperature sensitivity circuit maintains the laser device output constant average value by adjusting the diode of the current of the laser. In most cases, the LED transmitter design contain output power of the control circuitry. The laser device and the LED transmitters may also contain the cooling device maintained with the surface of relatively constant temperature. Most laser device transmitter either have the internal thermoelectrical cooler require relatively controlled external temperature because of the LED. The laser device requires more complex circuitry than the LED. The fiber optic transmitter, the laser device more expensive. For more information concerning the fiber optic transmitter and the driver circuitry, refer to the reference material listed in Appendix 2. Transmitter output interface generally fall into two categories: optical connectors, optical fiber pigtails. Optical pigtails attach the transmitter. Optical source of the pigtails generally routed out of the transmitter package coated fiber, then lost fiber buffer tube with a single fiber cable. The pigtail is either soldered or epoxy with the transmitter package to provide with the fiber containing leaf. The fiber tube single fiber cable is also attached to the transmitter package to provide additional strain relief. Transmitter output. The transmitter output interface must consist of the fiber optical connect with the optical source must be coupled to the optical output optical connect with the intermediate optical fiber. The one end of the optical fiber that is attached to the source. The other end terminates with the transmitter optical output connector. Optical source must couple the optical connector without the intermediate optical fiber. The optical source placed in the transmitter package belongs directly into the fiber with a mating of the optical connector. In some cases, the lenses are even more efficiently coupled to the light with the source and the mating optical connector. Fiber optic transmitter package. The fiber optic transmitter comes with various shapes and sizes. The least complex fiber optic transmitter typically be packaged with the transistor outline cans. Fiber optic microcircuit modulated with dual inline package within that single transmitter may require the simple separate circuit for the system and equipment that provide with the acceptable input signal to the transmitter. More complex fiber optic transmitters are available to have some of the all signal condition circuitry and integrate into the package of the transmitter. Typically, are packaged in hybrid microcircuit circuits modules over the dual inline package of the butterfly lead package circuit cards with a complete standalone fiber optic converter. The standalone fiber optic converter circuit cards generally contain the source over the transistor outline cans. One with a hybrid microcircuit package for the commercial application. For the most popular transmitter package is the transistor outline and the dual inline package hybrid microcircuit. The fiber optic transmitter application. Fiber optic transmitter can be classified into two categories: digital analog. The digital transmitter produces two discrete optical power level levers, so that essentially on and off, with the exception of the source of light. The minute the off state with some of the transmitter analog transmitter continuously vary with the optical power level, the function of the intended electrical signal. Digital application, a different type of the fiber optic transmitter, the digital, different digital application for each of the application, the link rate, data rate, with the transmission length, with the operational environmental influence, or for the type of the current wavelength, spectral width, and package type chosen for low data rate application. Fiber optic transmitter generally with the use of the LEDs operating either at 859 and 1300 nanometers window as their source of the low data rate 0 to 20 megabytes per second. The source tends to operate at 850 nanometer window with a moderate with 50 to 200 megabytes per second. The tend to operate at 1300 nanometer window. Laser sources are also never used the low data rate application. Laser sources are used only with extremely high transmitter with the output power with required in this application. The package found in the low data rate applications include all the packages of the type that discussed earlier. High data rate application, most fiber optic transmitter light diodes source with the source of typical operate in either 1300 nanometer, 1550 nanometer windows. Most high data rate application of laser devices as optical source operate in 1300 nanometer region. Almost 1550 nanometer systems use the light laser devices as the optical source. 1550 nanometer transmitters use only with extremely long distance high data rate applications, undersea link, etc. High data rate transmitter generally hybrids, microcircuit modules, complete circuit card with almost all the high data rate transmitter transmitter contain power to control circuitry. Depending upon the application, high data transmitters might contain the coolers. Alright, analog application for type of the fiber optic transmitter. I'll give the different analog application for each for the specific application. Analog signal type of the transmission length with the operating environmental influence source of the type, central wavelength, special width, and the package of the type chosen. For low frequency application, analog fiber optical transmitter of the general of the LEDs operating with either 859 nanometer, 1300 nanometer window, and take the low frequency application analog and audio and signal channel video system. The system source at the time to operate at 150 nanometer window for moderate frequency application. Sort of tends to operate with a 1300 nanometer window. These type of systems include multiple channel analog audio and video systems, low frequency modulated system, laser sort of also must never be used in lower modulated frequency analog applications. The main reason for this added is that the circuitry complex with the laser source required with the laser source are only with extreme high transfer output powers required with the application. Most for low frequency the analog transmitters are hybrid microcircuit modules, circuit cards, and standalone boxes. For high frequency application, analog fiber optic transmitter with the use of laser diodes, typical high frequency application cable television line with radar, raw radar remoting application laser device typically operate with a 1300 nanometer, 1550 nanometer window, 1500 nanometer window. Transmitters typically use a cable television trunk line application. Other applications may either be 1300 nanometers, 1500 nanometer laser device. High frequency transmitter with a predominantly circuitry card, but some of the hybrid circuitry circuitry models are used all high frequency analog transmitter of the TE coolers or linearization power control circuitry. Alright, Chapter 6 summary. Chapter 6 summary.